Hello students, let's start now Module 4, Celestial Mechanics. We studied with Kepler's laws how the planets move. Celestial Mechanics answers the question of what is causing the planets to move. So the learning objectives for this module is to connect planetary motions with the causes of these motions, explain the orbits as a consequence of gravitation, and connect the orbital elements with conserved physical quantities. So let's start from Kepler's third law. The law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. So this law implies something interesting about the velocity of the planets. If you consider that a planet is in a circular orbit of a radius r, then the circumference is 2 pi r, and the planet is traversing the orbit with velocity v with a period t. So if you equate the circumference with the orbital velocity times the period, you have that the period then is 2 pi times the radius over the velocity. For a constant velocity, then you would have that the period would be proportional to the radius. Now that is not the case. Because of Kepler's third law, the period is proportional to the power of 3/2 of the radius. So you can only reconcile it if the velocity is proportional to 1 over the square root of the radius. So further from the sun, a planet's period is longer, not only because it has a longer track to run, but also because it is going slower. Now Kepler realized that this law suggests that whatever is keeping the planets in motion is something that emanates from the sun and wanes with the distance, like light. So if it is like the behavior of light, then let's imagine a gravity luminosity, call it Lg, that emanates from the sun with a constant rate. So as it flows outwards, it spreads itself over progressively larger areas. So at any particular distance r from the source, then the gravity flux, call it Fg, should obey the same equation that we found for light, which is that the luminosity is 4 pi r squared times the flux. So we can solve for the gravity flux. So the strength of gravity should be related to the flux of these mysterious entities that are emanating from the sun. Whatever it is, its strength must fall with the square of the distance. This is the origin of the inverse square law. So in the same way that you have for light, the same amount of light is expanding spherically outwards and crossing progressively larger areas, the same thing would be happening with gravity if it is something that is emanating from the sun, like light, and geometrically diluting with distance. As distance increases, then the same energy would be spreading through a larger and larger area. Then you would have gravity following an inverse square law. So ultimately, the inverse square law is a consequence of the universe being three-dimensional. And this insight, in fact, predates Isaac Newton. Now, Kepler's third law has other interesting consequences. Newton specifically found that a pendulum behaved like gravity. If you consider again the period being 2 pi over omega, and you square it, and now substitute Kepler's third law, multiplying now both sides by omega squared, the right-hand side is a constant. So the left-hand side is also constant. If you divide it now by 1 over r squared, we find that whatever falls with r squared is omega squared times r, which was already known to be the modulus of the centrifugal acceleration, as derived by Christian Huygens in his analysis of the pendulum. So could it be that gravity and the centrifugal force were identical? That is a question that intrigued Isaac Newton. He considered the motion of the moon and calculated the centrifugal acceleration that it's subjected to. So Newton computed the centripetal acceleration that the moon was experiencing. He knew that it was omega 2 times r, write it as v squared over r, and the velocity of the moon is about 1 kilometer per second, and the distance is 400,000 kilometers. So that gives about 2.5 times 10 to the minus 3 meters per second squared. As for the gravity of Earth's on the moon, it should be the gravity that is experienced on the surface of the Earth, scaled by the square of the distance to the moon. Here, g Earth is acceleration of gravity on Earth's surface. R Earth is the radius of the Earth, and R the distance to the moon. So plugging in the numbers, the gravity on Earth is 9.8 meters per second squared, and the distance to the moon is about 60 Earth radii. So that gives you 2.5 times 10 to the minus 3 meters per second squared. Bingo. Coincidences in science are very suspicious. The conclusion is momentous. The force g Earth that makes stuff fall on Earth is the same force that is keeping the moon in its orbit. So Newton wrote about this. He said, in the same year, 1665, I began to think of gravity. From Kepler's rule of the periodical times of the planets being a sesquialterate proportion. Sesquialterate only means 1.5. Being a 1.5 proportion of their distances from the centers of their orbs, I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve. So 1 over r squared. And thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the Earth, and found the answer pretty nearly. Now notice that Newton wrote that in 1665, right? Newton was born in 1642. So here, Newton was 22 or 23 years old. That was young Isaac Newton. Now, knowing that the force falls with the square of the distance is not yet solving the full problem. The full expression of the force of gravity as we use nowadays is found when Newton's laws of motion are considered. First, the force is vectorial. It is a radial force that is attracting the body to the sun. So its vector expression must be a radial force pointing to the sun. Now, according to the second law, a body of mass m1 is accelerated by a force f1 according to F equal ma. So you can write the acceleration a1 as f1 over m1. Yet, if a is caused by gravity, Galileo's reasoning and experiments had already shown that bodies of different masses fall with the same acceleration. Galileo found this by an ingenious thought experiment. Imagine that you have two spheres, 1 and 2, that have different masses, with m1 being less than m2. Now, if the heavier sphere were to fall faster, then if you attach them together, sphere 1 would slow down sphere 2. So the resulting velocity will be between the velocities of v2 and v1 that the spheres would attain if they were released individually. That's the situation that is sketched here on the left-hand side. Now, you can imagine also that the two spheres attached actually result in a single object of mass equal to m1 plus m2. Now, in this case, if the velocity is bigger, if the velocity depends on the mass, then the whole ensemble should attain a velocity that is bigger than either v2 or v1. So the only way to reconcile the paradox is to have the velocity equal to v2 and v1. So all bodies follow the same velocity independent of their masses, and they are thus subject to the same acceleration. So going back to Newton, that means that this acceleration A must be independent of mass. So the only way to have F over m not depend on the mass is if the force of gravity is proportional to the mass itself. So we found another proportionality. F must be proportional to minus m over r squared. Now, according to Newton's third law, if a body is feeling this gravity, then the source of that gravity must feel an equal and opposite force. So the planet is feeling this force. Now, the sun is feeling a force F2, which is equal to minus F1. That is, F2 must be proportional to m1 over r squared. Yet, because of the second law, F2 must also obey F equal ma. And the acceleration A2, because it is gravitational, must also be independent of the mass m2. Therefore, F2 must also depend linearly on m2. So we can write A2 is equal to F2 over M2. And again, because A2 is gravitational, must be independent of the mass M2. That means that F2 must depend linearly on the mass M2. Now I have the situation that F2 is proportional to M1, and it is also proportional to M2. The only way that both can be true is if the gravitational force is proportional to both masses, M1 and M2. Now, if you substitute the proportionality by a constant, say big G, you find the full expression of the gravitational force. The proportionality constant, big G, is the universal gravitational constant, and this law is known as the universal law of gravitation. The value of G was measured later to be 6.67 times 10 to the minus 8 in CGS units.